Right, year 12. I just want to show you this quick bit of maths for potential divider circuits. So we'll draw a potential divider circuit. So there's a battery and the battery provides an EMF. And a potential divider circuit has got two resistors, and I'm going to call one big R and one little r. So that could be any value resistor and that could be any value resistor. And we could put an ammeter in the circuit, but we'll just say that the current flowing in the circuit is I. Just say that that's I. And also the potential difference across each resistor. So the potential difference across this resistor, if we put a voltmeter there, that would measure the potential difference across capital R. And if we put a voltmeter here, that measures the potential difference across little r, the smaller resistor. Okay, so they're the symbols we're using for this potential divider circuit. Okay, what maths do we know? We know that the sum of the potential differences will give the EMF. So the EMF will be equal to VR, the potential difference across one resistor, added to the potential difference across the other resistor. So we know that that's true. We also know the total resistance of the circuit. The total resistance in the circuit, you just add up the two resistances. So the total resistance in the circuit is just that. Okay, nice and simple so far. Right, what about the current in the circuit? Well, we know that the current in the circuit is the EMF divided by the total resistance. So that is the EMF divided by total resistance, we could write as R plus R. Okay, so you could do all kinds of calculations for any kind of circuit to do with that. What else do we want to know? We might want to know what's the potential difference across this resistor. So V capital R will be the current that flows through the resistor times the resistance of the resistor. Okay. We might also want to know the potential difference across this other resistor. Potential difference across little r, that's going to be the current flowing through it, which of course is the same current, times its resistance. Right, so that is kind of all the setup of the maths that we know. We can now see why the potential divider circuit works the way it does, because if you wanted to know, well, what is the ratio between the two potential differences? We know that they add up to produce the EMF, but what's the ratio between them? What if we tried doing this ratio? Well, VR is on the top of the fraction, that's I times capital R. V little r is on the bottom of the fraction, that's I times little r. And you can see that the current cancels, and then what you end up with is the ratio of the potential differences is the same as the ratio of the resistances, which is exactly what we said in the potential dividers lesson. So the ratio of the potential differences is equal to the ratio of resistances in a potential divider circuit. So that's nice, but we can do some other stuff as well. Okay, what else can we do? We can use this expression for the current here. We can use this expression for the current in this equation here. So the potential difference across this resistor is the current times resistance, but this is the current. So instead of current, we can put this, EMF over the total resistance. I might keep it as I'll keep it as R plus R. So all of that together is the current times R. Now we could just rearrange that. A little bit. That equation can be rearranged if we divide by the EMF, and that R will just go on the top of the fraction. So divide by the EMF puts it down here, that's the left hand side. And then this is already kind of on the top of the fraction. Can you see this is another ratio? The potential difference across the big resistor as a fraction of the EMF. So the potential difference across the big resistor as a fraction of the EMF, this potential difference as a fraction of the total potential difference, is the same fraction, the same ratio, the same proportion as the resistance of the resistor compared to the total resistance. So that potential difference compared to the total is the same fraction as this resistance compared to the total. So that's another kind of ratios thing. And of course you can also do exactly the same thing with this one. If we want to know the potential difference across this resistor, across little r, that is just the current times little r, but here's the value for the current, EMF over R plus R. This time we're timesing by little r. And if we do exactly the same rearrangement, we end up with, so divide by the EMF, so the potential difference across that resistor as a fraction of that entire EMF, and we're left with little r is on the top, divide by the total resistance. So exactly the same thing. The ratio between the potential difference across that resistor compared to the total potential difference, the EMF, is the same ratio as that resistance compared to the total. That resistance compared to the total. So that is a little video on the maths of potential divider circuits.